All right, let me speak about the heading again. So that we will gonna cover level 7 for today. And let's start with the disassembly first. So can you all see my screen correctly?
Yeah.
Nice. Oh, no, I should turn on the GDB first, right? So we can get into GDB. This is main, then we can see this code. And now I believe like you guys can easily identify like this kind of the code. So it will print up this address and then call password. So maybe we are more interested in like this password function. So let's get into there first. Then copy the text. I will reduce the size. Then copy all the text. Get it back. So I got all the disassembly. And one of the tips for like the quickly analyzing the program is that like if we can cut this kind of the disassembly at the end of like each function call, then what we need to do is just identifying like what kind of arguments were there, right? So let's try to do that kind of the method. So starting with this memset. So we know that the memset has 3 arguments: destination, value, size, right? And then now the problem is like identifying what is the first, second, third argument. And argument passing is done over like the positive indexing over ESP. So this will be first argument. This will be second argument. And then this will be third argument. Yeah. And then you can ignore all the like the storing over EBP at this time because the EBP is setting up some of the storing the temporary variable to the our stack frame, or like we can the program is storing some of the local variables. And now we can change this to destination as the first argument was ECX, and then the second argument is 0, and then third argument is 0x200. And we can easily assume that the ECX will point to a buffer size as a 512 because 0x200 hexadecimal is like a decimal 512. And next is to like get the where this ECX comes from, and we can easily see that a few lines above, LEA EBP minus 20C. So we can simply change this as EBP minus 20C. And if we translate this as a C-like pseudocode, then we can safely assume that we have a character buffer EBP at EBP minus 20C, and its size as 0x200 because we could get that information from the memset argument. Is there any question up to this point? Maybe not. This is like what we have done previously too. And then let's move to the next function. And we have scanf function. And what we know about the scanf is we will have a format string here, and then some of the variable arguments for the scanf. So we could have like one or many arguments depending on the what kind of format string that we use. For example, if we use just a %d, then we will have one additional argument. But if we have %t, %d, then like we should have 4 additional arguments. So to get the idea of like how many arguments we have for this kind of the scanf or printf, that kind of function, we need to identify the what is the first format string and then take a look at the value. And to do that, we need to identify the arguments. So this will be second argument because it is like the x over ESP plus 4. And this one as like the EAX should go for the right at the ESP. Then this will be the first argument. And then we know that the second argument comes from EBP minus Q1C because this will go to ECX. Yeah. And then that is the second argument. And then EAX is from EBP minus 218. And then this goes to EAX and then goes to the first argument. But that would not be the answer that we want because we want to know that, for example, mostly we use a scanf something like this. If the format string is %d, then we use it something like supplying the address of the variable to store the variable in the stack or some of the global variable or something. So we should pass some of the address here. And also for even if the case is like getting the string %s, we put the buffer address here. So we usually use the pointers as the additional variable arguments. And then right now, the access pattern of this one, like the move this variable to EAX. So no, the second one. So move this variable to ECX. That actually moves the value, not the address. But what we need is address for this kind of thing. And same thing for the first argument, because the first argument is a string, then it's another character pointer. So we should hand over some of the pointer, but these are not the pointer. So in that case, we need to analyze where these values are coming from. And then, is there any question? No. Then I will go little, I will try to take a look at the little lines above. Then the EAX was coming from this EAX stored at the EBP minus 218. And then ECX was coming from ECX EBP minus 21C. And then you guys will see you might think this kind of code is quite redundant, but this is due to this Spiner program is not that optimized. That's why. And then the reason why I didn't apply optimization is if I apply that, for example, -02 on GCC, then you will see the totally different assembly lines. Then that actually make you to have a more difficult reasoning about to apply the reverse engineering. So I intentionally turned off that kind of the optimization to have just applying the very basic reverse engineering technique to get this somewhat pseudocode of the program. And then let's try to take a look little about where we get this kind of the values. So here, yeah, we have LEA, this address to EAX. So in this case, we could store address of this one to EAX, and then this EAX goes to EBP minus 218. So right now, let me remove all the scanf here. So we have scanf, EAX, ECX. And we know this EAX is coming from here and coming from this EAX, and that EAX is from here. So this address, and then this ECX coming from EBP minus 21C, and then from here, and this ECX is coming from here. So we know that EBP minus 20C is the buffer that we apply memset here, and then This is the format string. And we previously defined EBP-20C as a character pointer buffer based on the what we have seen from the memset function. And then let's check that. So if the format string is a %s or something, then that assumption is true. So let's open GDB on the right side. And to check the format string, because we know the type of this one from the function signature of the scanf. And that's this one, %50s. So it gets up to 50 characters from the user input, and then put that onto the buffer argument. Yeah. That's good. And then next is about printf. And now I believe you can easily analyze this. So printf, and the first argument is this one. So we can just get this address. So your buffer, it says like this. And then the second argument is at edx. So EBP-20C, the buffer. So it will just print out what we just supplied here and here. That's it. And then the next function is string length. And it has just one argument. And here's another unoptimized code. So it will move ESP to EDX. So we should regard EDX as an ESP. Then the first argument will be ECX. And the ECX gets the LEA EBP-20C, so the buffer. So it will get the length of the string. And then the next function is memprob. And I'm not sure you guys know about what is the, sorry about that, what memprob does. And in case you don't know about the memprob, then you can try it memprob. Then it will show you that what this function do. And then it has two arguments. One is pointer, and then the other is a length. So we can safely assume that it gets some of the string length, and then it has some of the buffer. So maybe the code will put the EBP-20C here, and then length of the string here to apply some of the thing. And then what this function is doing is from the description, the memprob function encrypts the first n bytes divided by the size of the memory area S by applying XOR each character with the number 42. So this actually does not do any kind of encryption because it is not secure at all, but it just changing the value by applying the XOR with the number 42. So it's some of the, I believe it's this kind of the function is there for just for fun. And I'm not sure what's the actual use of this one, but I know that the function exists there. So I applied that to skew your brain a little bit when you solve the level 7. Yeah. But this is an easy one. Just if you apply another XOR each character 42, then you will get back the original text. So that's the thing you need to solve. And after identifying this, so we will do the same thing. So we will call memprob. And then the first argument is ECX. And this ECX is coming from EBP-2030. And then that was stored at here. And then this ECX is actually same as this one, which is coming from here. So that's same as the buffer. Yeah. So from the simple analysis following the assembly lines and then register values, you can see that EVP minus 20C will be the first argument. And then second argument is EAX. And EAX is coming from stored at the EVP minus 210, but just EAX. Then there's no other reference here, but the EAX is stored here. But the important thing is that whenever you call a function, the return value of the function will be stored in EAX. So right after calling this one, we might expect there will be some of the return value, for example, something like this. And then this value will be automatically stored in EAX before returning from this function. So EAX now stores the length of the string. So that will be stored here, and then that will be put on the second argument of the memprob. So we can write it as this. So this will apply XOR number 42 to each character of your input. And then there's a function, add a space, and the first argument is ECX, and then that is EVP minus 20C, so something like this, and then there will be no other arguments. And here, important thing is that you will see that from the printf function, you will see printf at PLT, string length at PLT, memprob at PLT. But for this function, you will not see PLT here. So what PLT stands for here is like this is a procedure linkage table, and then we will not gonna go over details about what is PLT at this time, but we will learn that around the week 4 or 5, because we will use that to exploit some of the vulnerabilities. But at this time, we will not gonna cover that. But what you should know at this time is that if the function name is with the at PLT, that means the function was included from the library, external library. So from the C standard library, so when you code something in C, the first thing you should do is like a shop include as stdio.h or stand.lib.h, something like that, right? So some of the function defined in those headers are like in the so-called libc, the external C library. And if those are in there, then you will see this kind of the at PLT, because it's calling through the procedure linkage table to access the library function. But here, we do not have any at PLT here. That means this is another defined function in the binary program. So we need to get the disassembly of this one. So yeah, this is the disassembly of the add a space. And let me do it something like this. I think it's not good for copy and paste. So let me create another window. Copy it. Go back. And go to here. Yeah. So this is another assembly. The space. And then let's try to analyze this function. So we can easily get that these 3 lines are function prologue for moving the stack frame down from the making the EBP down to ESP and reserve the ESP space. And then do some of the operation. And then there's a compare and jump. And then there's a jump and then return. So the reason why I try to focus on the jump or like compare this kind of thing, it's like if there's no other function kernel here, then in that case, like the better way to get the structure of the program is like the try to know about the program flow. Yeah. And then the program flow changes whenever we meet the if, for, while, that kind of the loops or like the conditional statement. And those conditional statements starting from the compare and jump or just a jump. Yeah. And let's try to analyze this compare and jump first. Then it compares 0x0 to EAX. Yeah. And then where this comes from. So this EAX comes from MOBSVL, ECX, EAX1 to EAX, and then we should focus on the ECX. So maybe you guys are curious about like what this instruction means. So if you search about like an MOBSVL on Google for with the x86 as a suffix or something, then you will see that this is a move signed extension byte from long. Yeah. So from the long address, it will just access 1 byte, and then it will store into the 4-byte register. And then the important thing here is that the access pattern of this one is ECX. And then if we change this kind of access to the C-like access, then this will be EAX multiplied by 1, something like this. Yeah. And then that will be stored to EAX. So if you just follow this kind of the simple translation, then you could have better understanding about this kind of assembly line. Yeah. And to get that, you need to understand what these means. And then from the slide in the lecture 2, you will see that the negative and accessing over indexing over EBP is about like the passing, no. It's about setting the local variables, but the positive indexing, yeah, over the EBP will be getting the argument from the caller. Yeah. So EBP plus 8 actually means that the first argument stored for the supplied to the function. So for example, we can expect that the addr space will have a 1 argument, and then that the first argument. So maybe we could name it as a first argument, and then here EAX will store first argument. And then EBP minus 4 will store first argument, and then EBP minus 8 will store 0. Yeah. And then EAX will store 0 because it's EBP minus 8. And then ECX will store the first argument. Yeah. Now we can change this line. So ECX was first argument. And then EAX was 0. So EAX will get the first byte of the first argument. Yeah. And then it will compare that first byte with EAX. Yeah. And then if that is equal, then, so for example, we can write this as if something like this. But the two, because it will jump out and then move to here. So this is the function epilogue. So to include the assembly lines below, so we can negate the condition and write the code like this. Yeah. And then we have this code again. Yeah. And we know that the EBP minus 8 was 0. Yeah. So EAX will get EBP minus 8. Yeah. ECX will get the EBP minus 4, but that's the first argument. And then what we will do is first argument accessed by EAX multiplied by 1, EBP minus 8. Yeah. And then store that to EAX. And then for EAX, it will do add the 0x20. And then for EAX, and apply the AND operation of the with the 0xFF. And can you guys know like what this operation do? So the function name is called add a space, and actually this white space character, its ASCII code is exactly same as 0x20. So the number 32, hexadecimal number 0x20 is an ASCII code of white space. So the function name is quite explicit. It will add a space to a character of the first argument. Maybe this will be the buffer. And then the reason why it ends with the 0xFF. So for example, if we have a sum of the value, for example, 0xF0, and then if we add this with 0x20, then this will be 0x110. Yeah. And if we end this one with the 0xFF, and then this AND operation actually will take the last byte and then make the rest of the bytes as a 0. So this will be just 10. So to make the result as a 1 byte, yeah, the code actually applies the AND with the 0xFF. So that's the reason. And then I just defined this as an if, but the thing is like it has a jump back to this line at a space plus 19. In such a case, we need to change it as a for, while, those kind of a thing. Yeah, and then if this is a loop, then right before having this kind of the jump back function, we will see the loop variable. And loop variable is quite eminent here. So EBP minus 8 will be the loop variable, and we have an increment by 1, add 1 to EAX, and then put that back to EBP. So now we have a better understanding of this function. So the loop starts at the code plus 19, and we would have 4, and then we will say int I is at EBP minus 8. So at the start, we set that value as 0 because here we put 0 at the EBP minus 8. Yeah. 0. And then the exit condition is, so we want to exit at first argument, and we access that with the EAX, and then that's actually from EBP minus 8. So that's I. If that is 0, then we want to exit. So if that is not 0, then we will continue. And then at the end, we have a loop increment here, just +1 to the variable. Then the code would be this or this, right? So we can rewrite that as a for loop. So I can remove this. And then what it does is, it will just do, because EAX is this one, and then now we will move, DL is the last byte of the EDX register. So DL will be, we will store the value of the AL. And then EBP minus 8 is now I. So EAX will be I. And then EBP minus 4 will be the first argument. So ECX will be the first argument. And then this move has another triplet-based memory access, and ECX accessed by EAX multiplied by 1 would be the DL. And then to interpret this one with a simple one line, we know that the ECX is the first argument, and then we know that EAX is I, and DL is coming from AL, so something like this. And now we have this here too. So we started with EAX was first argument I, and then do this one, and then this one, and then put that back to the buffer. And then it returns. So to understand this function more easily, then I will clean up our disassembly and decompilation. Yeah. So I will just copy all. And remove unnecessary parts. So I will basically remove all the disassembly. Then we know that how to interpret these. We also don't need this. So we can rewrite the function as function add a space. We'll get the character pointer argument. The reason why I say character pointer is that we know that it will apply the adding up the value byte by byte. So we see the triplet that the EAX multiplied by 1. So if that value is 4, then we could regard that as an integer, or if that is 2, then that will be word. But we see that this memory access as 1, so it will access byte by byte, so that we can assume that the type of this first argument would be character pointer or uint 8 pointer or something like that. And then internally, it will go over all the characters until it does not meet the null byte. So it will go over the string, and then if that does not meet the string end, then it will continue. And what it does is just for the value, yeah, it will add 0x20. So actually add a space and then make it to be 1 byte and then put that back. That's it. So that's what this add a space does. And then after having that transformation, so right now, not too confused about the thing, so let's get back to the original code. And then we have a buffer at the EBP-20C. So please recall that, because we will reuse that variable in the original code. So we just called the add a space and then just got back to the original password function. And here we call A2I. So you guys might all know about what this function is doing. So it just changed the string to a number. So string-based number, so number 1, 2, 3, 4 as a string to integer number 1, 2, 3, 4, for example. So in that case, it will supply. The first argument is from EAX. That's EBP-20C. So after transforming our input with the memfrub and then add a space, then it will change that as an integer value. And because we might expect that the program will use this integer value, so maybe we can store that as a int value. And then like same thing. So after calling a function, the return value will be stored into EAX. So we will see move EAX to EBP-214 here. So we can safely assume that value is at the EBP-214. Yeah. And the next function is printf. So we know that printf format arguments. And the first argument is coming from ECX, so this one. So the string is like a your integer, so it will show the intermediate value, what it has. And then we can expect that there will be one additional argument as an unsigned integer, because it's a %u, so unsigned to decimal value integer. And then the second argument is coming from EAX, and that EAX is coming from the return value of the ATY. So we can write it as value. And the next is SNPrintf. And for SNPrintf, we need a target destination buffer. So SNPrintf is like a running printf and then store the result into the string buffer. And then this n means the maximum size of the output. So size, and then format, and variable argument will be here. So if you don't know about like this kind of the function signature, you can easily run mem_printf. Then you can see the function signature of this one. So this one actually. So it has a destination character pointer and the size, format, and other variadic arguments. So you can easily get the template of the function. And then let's get the arguments. This will be first. And then first argument comes from EBP-20C from ESI here. and then that's LEA, so that's the right address. EBP minus 20C will be here. And then second argument is the size. 0x14 is 20 in the decimal. And the format string comes from EDX, and that's at here. So what it does is a %X. So it will change it as a hexadecimal string. And then what is the last argument? EDI. And EDI comes from EBP minus 214. And then that was stored here. Yeah. Then that was stored here. So we know that the EBP minus 214 is the variable value that we got from A to I. So this will be something like this. So now it's something like, after getting the string, get length, it will run memprob and run add a space and change that to an integer value as a decimal, and then change that as a string of that value as a hexadecimal string. Yeah. And then this will be another printf. Maybe it will just printf hexadecimal value for your help, right? Your hex integer, right? And the value will be, string will be, the second argument is from EDX, so EBP minus 20C. And the next call is the string length. And this will be the same as like how we did. So ESP will be EDX. So this will be the setting the first argument. And that's also EBP minus 20C. And then next is memprob. We know that the length will go to the EAX and here, yeah. And then that will go as a second argument. And the first argument will be ECX, but that didn't change. No, that is from EBP minus 248, but that is coming from here. And that's EBP minus 20C. So it will apply memprob EBP minus 20C, yeah. And then length. And then it will do add a space again. And the first argument is from EBP minus 20C. And then we are about to getting to the end. And then this one. So it will get EBP minus 20C to EAX. So we can regard that as EAX will store the address of the EBP minus 20C. And then this move is not move ZBL, SBL, those kind of thing. So it will move, access the EAX, and then read 4 bytes, and then store that to EAX. So how we can regard this as, we define character pointer EBP minus 20C as something like this. But what we do right here is like we will access 4 byte and then store that to EAX. So 4 byte type would be something integer, something like this. And we can say this something like, maybe it will be better to have another variable. So the first EAX here, so we can have this as a integer pointer EAX, and that will be integer pointer EBP minus 20C. And then the next EAX will be int value EAX, and then that will be, no, not this one. The difference of int PTR EAX. Maybe the better one would be something like this. So because this move is like moving 4 bytes, because the destination is the EAX register. So even if the assembly line omits the MOV L at the end, so we can safely assume that it will copy 4 bytes. So we need to translate the code like this. And then it will subtract some of the value will be value EAX minus something like this. And then, so this instruction, if you search this instruction on the Google with the set NE x86, so it will set the registered VL value as 1 if the current condition is not equal, and then it will set 0 if the current condition is equal. And equal and not equal, how it works in the Intel x86 architecture is that the NE is actually same as NZ. And E is same as a Z. This is because how the CPU compares the number is that like if we want to compare a number A and B, and how the computer compares the number is like it will just calculate A minus B and then test if that's a 0 or not. If that is 0, then we know that the two numbers are equal. And if those are not 0, then the result is not 0, then we know that it's not equal. So actually the semantic of the not equal is exactly same as a not 0, and then equal is same as a 0. Yeah. So we actually subtract the value, this value from EAX, and then we can regard this as a set NE as a set NZ. So it will just test the 0 or not. Yeah. And then it will move the 1 byte to ECX and then compare that with 0. So this is actually the condition is if value EAX equal to what is that? ECX. ECX is coming, so ECX is coming from here. So that will be the result of this subtract, and then if that is 0 or not. So value of EAX minus. So we want to test something like this. In that case, we can actually make this condition like this. If we just move a subtract point to the opposite side. Then, so the condition is a jump not equal. So if we make it as an equal sign, then we can include all these lines. And then these are the test fail condition. Yeah. So it's something like this. And then function end. And for these printf, we can analyze it like this. It says, oh no, for the else condition. And then for this one, printf. It says we got the password. And call get a shell. Like this. And then let's collect all the assembly lines to get a better idea about what's going on. So I will do some of the dirty thing to remove all the assembly lines. So we have a character pointer, memset, scanf, printf, get the length, memprob. Then we don't need all these things because what we need is just an add a space, is adding a space. And ATY, printf, send printf, printf, string length again, memprob again, add a space, and we have a 4-byte access. Then we have an if condition. We don't need these. We need this. Something like this. And let's take a look at that in one screen. Yeah. So this is the code of the program. And what we should match is like the final value of the EAX should be this value. And then that value was coming from this one. And then that was the result of the add a space and then memprob of the, and then that's should be the hexadecimal integer. And then that should be the result of the ATY. And then that should be result of the inverse of the memprob and add a space and memprob, and that should be from our input. So what we need to do to get the what should we put at here is that we can apply the reverse step of the each by each. So for example, so the first thing is that we know that final value should be this one, yeah. And then that value should apply add a space and memprob. So in that case, we can actually write some of the script to solve the problem. For example, so I will write a Python script. And to change this kind of the integer value to a string, we can use a library struct in Python. And then if you do struct pack, and then right now we have an integer value of 0x683333A3E. Yeah, then we will get the string. Then let's try to print it. Check if it gives us the result. So seems like we need to find a way to like having these characters right after the add a space transformation. Yeah. So now we have the string. Yeah. And then to inverse add a space, we can create a function called maybe the inverse of that one, sub a space, and then we could have a binary string. Because the result was the binary string, right? Yeah. And then what we can do is maybe I can just use Python 2. So in that case, you guys don't need to play with the binary string at all. Yeah. And here, add a space was like adding the 0x20. So what I will do is, so we have a string and I will create a new string as an empty string. And for character in string, how would we return set? So let's do, let's run it first. What was the error? Yeah, so it just print each character. So we can get the ASCII code of the character like this, and the sub space, we will subtract 0x20. Yeah, and then we will make it as a character back like this. And then we will add it back to the new string. Yeah. So the intermediate result by inversing this code will be like this. I did not return the results, so that's why. Return new string, okay. Then it has some of the string, but not printed it well because it's before applying the 0x, before applying the memprob. And then another function is like the inversing memprob. So we need to define a function as inverse of memprob. And then that is, we will have a new string. It's this one. And for character in string, so new string will have character of this one. So because memprob XOR each character with 42, so we will apply XOR with 42 again. Then we will have the original string. So return the new string again. And then what we will do is apply memprob again. And yeah, we see some of the value here. Yeah. And then that should be result of the hexadecimal integer. Yeah. So to inverse SM printf. So we need to put some value here to generate 409b. Yeah. So in that case, it's quite easy. So the integer value we should generate is 0x49 is 409b. So we need to translate that string as a hexadecimal integer. Then so the number we should generate is like 16539. That should be supplied at here. Yeah. And then that's the value we want at the A to I. Yeah. So string of int value will be the buffer before A to I. Then I will print it again. Maybe it will print the same thing as a string. The difference is like that I just change the type from the integer to string. Right? 16539. And then we will apply inverse of the added space and then memfrob again. Then we will finally get the input that we should put at here. So now we have sub a space buffer before ATOI and 3, and then we will apply inverse of memprob. Yes, and let's print. So it says something like this. Maybe this is weird, but let's try. It worked, right? So after analyzing this program, so what it does is like if we put this number, then it will first apply memprob and add a space, then it will be translated as a 16539, and then that will be translated into the hexadecimal integer 409b, yeah, and then that will be translated with through the memprob and add a space, then what was that? These 4 characters, and then that'll be compared at here, then you can get a shell. And to actually get the thing, what we need to do is like we need to go over the inverse of the each approach. So what we did is like we first translate this comparison value as a string, and then apply subspace inverse memprob, and then change that, and then read that as a hexadecimal integer, and then convert that as a integer, decimal 1, and then convert that as a string, and then apply subspace and inverse of the memprob again. Then finally, we can get the input that we should put to get the make the program execute tilde here and get a privilege shell, and you can get the group ID privilege here. Yeah. I believe like some of you have feel a little bit of difficulty about like the translating this kind of the number to like the as a 4-byte character, and also struggle with the like analyzing the add a space function, because like this was not a like library function at all. But I hope this tutorial provides like how can you distinguish the library function from in the function defined in the program. So the signature is like the verifying the @plt sign. Yeah, if that is not attached as a suffix, then the function is defined in the program. And then after you have all the code decompiled like this, then you can write a Python script to easily convert and then inverse each of the transformation to get the final result.